Hello. So what we're going to be talking about today is what's called extrema on an interval. So now we're going to be starting to get into areas of calculus where we actually talk about the different applications of derivatives and what we can use derivatives to help us find about a function. So the first piece of information that we're going to try and find about a function is its different extrema. And an extreme point or an extrema is just another way that we refer to minimums and maximums of a function. So an extrema is either just going to be a minimum point or a maximum point of a function. So what does it mean to be a minimum or a maximum? So f of c, so some y value is going to be considered a minimum for your function on an interval if that y value is less than or equal to all of the other function values for all of the other x values in that interval. So basically, it's just what your intuition is telling you. F of c is a minimum if it's smaller or equal to all of the other points inside of an interval. And just the opposite is true for a maximum. So f of c is going to be a maximum for a function on an interval if it is greater than or equal to all other y values in that interval. So pretty straightforward what you'd think of it intuitively. So now we have two different classifications of extrema. So we have what's called absolute extrema and then relative extrema. So absolute extrema are points that are either higher or lower than all other points. So when we say something is an absolute extrema, we know for sure that it is either lower than or higher than all other points in an interval. And we use this type of classification of extrema when we're talking about an interval because sometimes it's hard when you're talking about a whole function to say for sure if that point is lower than or higher than all other points for the function. So you're going to use the term absolute extrema on an interval. And the term relative extrema just refers to points that fit all of the criteria for being an extrema, but are not necessarily higher or lower than all other points. So you might be thinking, if I have an extrema point, but it's not higher than all of the other points on an interval, is it really an extrema? And the answer is yes, and we use this more when we're talking about just generally what's a minimum and a maximum of a function. And this is probably really confusing to you right now, but we'll define this more concretely in a little bit when we're talking about how to actually go about finding these extrema values. So what we have is this very important result from the extreme value theorem. So the extreme value theorem says that if we have a continuous function f of x on some closed interval from a to b, meaning that you have a y value for every x value between a and b and at a and b, then f of x will have both a minimum and a maximum value on an interval. So this means if you look at any continuous function and you look at a piece of it over a closed interval, you are guaranteed to have a point that's lower than all other points and guaranteed to have a point that is higher than all other points. So now how do we actually go about finding these extrema? Because that last theorem told us that they existed, but they didn't tell us how to go out and actually find it. So the first thing you're going to do is probably be wondering, okay, so we're in calculus class. So far, she hasn't talked anything about calculus. Well, this is where calculus is going to come in. So a extrema happens. So extrema happen when f prime of x, or your derivative of x, is equal to 0. You might be thinking, well, why is that true? So let's just draw a quick picture. Just got this random function. So minimums and maximums, those extrema points, they happen at the hills of your function or at turning points of your function. So different extrema points are going to happen here, 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 and here on this function that we have. So now if we draw the tangent lines to these extrema points, these minimums and maximums, I'm going to get something like this. Lines are a little bit off, that's okay. So we know that the derivative of a function gives us the slope of the tangent line points on the function. So if we look at these lines that we've drawn for the tangent lines there, they're all horizontal lines. And the slope of horizontal lines is always equal to 0. So in other words, when the slope is 0, we have a horizontal tangent line, which means that we have a turning point of our function. So that means that we're going to have an extrema point there, possibly. And what we really want to be careful of when we're testing for extrema is that we call these critical points. So in order to find extrema for a function, you're going to take your derivative, set it equal to 0, and solve for x. So our steps here are going to be to find f prime of x, set it equal to 0, so do f prime of x is equal to 0. Then our third step is going to be to solve for x. So find out what x values give you that point. And these x values, we call them critical points. They're called critical points because it means something is happening there at that point of the function that we probably need to examine a bit closer to see what's going on. So now, there are a few different ways to test that. So in this section, we're just going to be talking about finding extrema on a closed interval. So on a closed interval from a to b, this other step that we have to go about doing to find the extrema is now we have to actually find all the y values. So step 4 is going to be to find the y values for all of your critical values, for all critical points. And then we also need to find the y values for the endpoints of your function. So we're going to find f of a and f of b. And then all you're going to do is compare all of those y values. So then you're going to compare your y values to find the minimum and the maximum. Because the largest y value will be your absolute maximum on the interval, and your lowest y value will be your absolute minimum. So that's your basic process. So now let's actually go through and do some examples. So our first example is we want to find the extrema for f of x equals 3x to the fourth minus 4x cubed on the interval from -1 to 2. Okay, so our first step was to find our derivative. So step 1. So f prime here, it's pretty easy to find. It's just a polynomial, so we can use our power rule. So we're going to get 12x cubed minus 12x squared. So now we're going to set that equal to 0. So we're going to get 12x cubed minus 12x squared equaling 0. So when we set something equal to 0, now we're going to try and factor it if we can. So we have a greatest common factor between these two terms of 12x squared. So we're going to factor a 12x squared out, which is going to leave us x minus 1 equals 0. So since we have the product of two things equaling 0, we can set them both equal to 0. So we get 12x squared equals 0, x minus 1 equals 0, and now all we have to do is solve for x. So the first case, it's pretty obvious that we're going to get x equals 0, dividing by 12 and taking the square root, and then adding 1 over here. We're going to get that x is equal to 1. So our critical values for this function our critical points, critical values, whatever word you want to use, they're the same, are x equaling 0 and x equaling 1. So now because we're on a closed interval, we also want to look at our y values. So step 4, let's find all of the y values for our critical points. So let's find what f of 0 is and f of 1. So plugging in 0 to our original function, we're going to get 0 minus 0, which is going to give us a 0. When we plug in 1, we're going to get 3 times 1 minus 4 times 1, or in other words, we're going to get 3 minus 4, which is equal to -1. And now we also said on a closed interval that we needed to look at the y value of our endpoints. So we need to find f of -1 and f of 2, so that way we can compare all of these values. So when we plug in 1, we're going to get 3, and the -1 raised to the fourth is +1, so we're going to get 3 times 1 minus 4, and -1 cubed is -1, which means that we're going to get 3 minus a -4, or 3 plus 4, which is 7. And then when we plug in 2, we're going to get 3 times 2 to the fourth, which is 16, minus 4 times 2 cubed, which is 8. So we're going to get 48 minus 24, I'm sorry, minus 32, whoops, which is going to be equal to 16. So simple enough. So now that we have all of these written out, we want to see which one is our lowest point and which one is our highest point. Well, it's pretty easy to see that -1 is the smallest y value that we have, and that 16 is the largest. So for this function, we can write that we have an absolute minimum, or sometimes we abbreviate it this way, at the point 1, -1, and we have an absolute maximum at the point 2, 16. So sometimes, even though we get critical points, they're not necessarily going to be absolute extrema for a function. They might be relative extrema. So we could label the point 0, 0 as being a relative extrema on this interval. But usually when you're on a closed interval, you're just looking for absolute mins and maxes, which are just going to be your highest and lowest y values. So let's try another example. So find the extrema for f of x equaling 2x minus 3x to the 2/3 on -1 to 3. So let's go through the same process. So first let's find our derivative. So f prime of x is, again, going to be fairly straightforward just using our power rule. So the derivative of 2x is going to be 2 minus 3 times the derivative of x to the 2/3. So using our power rule, we're going to bring down the 2/3. X, and then we're going to do 2/3 minus 1, which is 2/3 minus 3/3, so we're going to get -1/3. So if we simplify this real quick, we're going to get 2 minus, these 3's will cross out, 2x to the -1/3. So our second step was setting it equal to 0, so we're going to get 2 minus 2x to the -1/3 equaling 0. So we'll add this 2x to the -1/3 to both sides. We're going to get that 2 is equal to 2x to the -1/3. Dividing both sides by 2, we can get 1 is equal to x to the -1/3. So that means that we can raise both sides. Maybe we want to rewrite this so we don't have a negative exponent. So we can rewrite this as 1 is equal to 1 over x to the 1/3. Which means that x to the 1/3 is equal to 1 if we cross multiply. We raise both sides to the third power. We're going to get that x is equal to 1. So our only critical value here is going to be x equaling 1. So maybe we'll label that as a critical point. Okay, so now let's go back and let's find, which that's step 3 usually. So let's go back and we'll find all of our y values for. So since we only have one critical value, we only have to plug in one x value for step 4. So let's find what f of 1 is. So that's going to be 2 times 1 minus 3 times 1 to the 2/3, which is just going to be 2 minus 3, since 1 to the 2/3 power is always 1, so we're going to get -1 here. So then all we have to do in order to find our absolute extrema is find the y values of our endpoints. So we need to find f of -1 and f of 3. Okay. So if we plug in -1, we're going to get 2 times -1 minus 3 times -1 to the 2/3, which is going to be -1 squared raised to the 1/3 power, which is just going to be -2 minus 3 times the cube root of +1 then, which is 1, which is going to give us a -5. Okay, so now let's plug in 3. So we're going to get 2 times 3 minus 3 times 3 raised to the 2/3 power. It's going to be 3 squared to the 1/3 power, which is going to give us 6 minus the cube root of 9. Now we can't pull any perfect cube roots out of 9, so that's as simplified as we're going to go. So if we use our calculator for a quick second to just see what that is. So that y value on there is roughly -0.2403. Okay, so now we just need to label our absolute mins and our absolute maxes. So this negative 0.2403 is actually the largest of all of our y values because it's the closest to 0, and this negative 5 is going to be our smallest. So for this function, both of our absolute extrema actually occur at the endpoints. So we can write that we have an absolute min at our lowest point, which was -1, -5, and that we have an absolute max when we plugged in the 0.3. So we're going to get 3, and then we don't want to write our decimal approximation. We want to write the actual answer there. So we're going to do 6 minus 3 cube root of 9. So there we go. Let's do one more quick example and see what we get. So we're pulling in some trig here. So sometimes these get a little harder when we're talking about trig functions. But we want to find the extrema for 2 sine of x minus cosine of 2x on the interval from 0 to 2 pi. Okay, so same process as before, even though it's trig. So we're going to start with our derivative. So we're going to do f prime of x equals what? So the derivative of 2 sine of x is just going to be 2 cosine of x minus the derivative of cosine of 2x. Now for this one we have to use our chain rule. So first we're going to do the derivative of cosine of 2x, which is just going to be negative sine of 2x, times the derivative of the inside, so the derivative of 2x is 2. So our final derivative here is going to be 2 cosine of x plus 2 sine of 2x. Okay, so now we're going to set that equal to 0 and solve for x. So 2 cosine of x, forgot my x there, plus 2 sine of 2x equals 0. We can divide everything by 2 and get rid of those things. So we're going to get cosine of x plus sine of 2x equals 0. So now what we're going to do is we're going to use a trig identity on the sine of 2x. Having a sine of 2x is kind of hard to solve for, so we're going to replace it with something else. So we're going to leave this cosine of x alone, but the sine of 2x is the same thing as 2 times the sine of x times the cosine of x. So now we have something in common between the two terms. We have a cosine of x in common. So we can factor a cosine of x out, which leaves us with a 1 plus 2 sine of x equaling 0. So now we're just going to set both terms equal to 0 and solve those. So we'll have cosine of x equals 0, 1 plus 2 sine of x equals 0. Okay, so solving the first one, we want to look for points between 0 and 2 pi that have a cosine of 0. So we're looking for angles that have a cosine of 0, which means on our unit circle, we're looking for points that have an x-coordinate of 0, which this is going to give us that x is equal to pi over 2 and 3 pi over 2 using our unit circle. And if we solve this equation over here for just what sine of x should equal, we're going to get that sine of x, 2 sine of x is equal to -1, or sine of x is equal to -1/2. So now we're going to be looking for points on our unit circle that have a y-coordinate of -1/2, which means we're going to be down in the third and fourth quadrant. So we're going to have two answers again. So let's try and figure out what they are. So x equaling -1/2 means that we have a cosine of √3/2. So that means we have a bigger x-coordinate than our y-coordinate. So we're going to be at 7 pi over 6 and 11 pi over 6. So we have 4 answers to check out here. So going back in, we're going to plug all of these critical points in to our function. So our function was 2 sine of x cosine of 2x. So maybe we'll rewrite that down here. Two sine of x minus cosine of 2x. Okay, so let's find all of our function values. So we're going to do f of pi over 2 first. So f of pi over 2 is going to be 2 times the sine of pi over 2. Well, sine of pi over 2 is 1, so we're going to get 2 times 1 minus cosine of 2 times pi over 2. 2 times pi over 2 is just pi, and the cosine of pi is negative 1. So we're going to get minus negative 1, which is going to be equal to 2 plus 1, or 3. Okay. So now let's do f of 3 pi over 2. It's going to be 2 times the sine of 3 pi over 2. So we're going to get 2 times negative 1 minus the cosine of 3 pi. Well, 3 pi is the same thing as pi, so again, we're going to get negative 1. So now we're going to get negative 2 plus 1, which is negative 1. So now let's plug in the other two values that we have. So f of 7 pi over 6. We know that sine of 7 pi over 6 is negative 1/2, so we're going to get 2 times negative 1/2 minus the cosine of 7 pi over 3 if we multiply that by 2. So 7 pi over 3, let's figure out what quadrant that's going to be in. So 7 pi over 3 is actually bigger than 2 pi because we can pull out 6 pi from the top. So we're actually 7 pi over 3 is the same angle as pi over 3. So now we need to know what the cosine of pi over 3 is. The cosine of pi over 3 is just going to be 1/2. So here, 2 times negative 1/2 is going to give us negative 1 minus 1/2. It's going to give us negative 2 over 2 minus 1/2, or negative 3 over 2. Okay, so one more to go. So now let's do f of 11 pi over 6. So we know from when we solve for 11 pi over 6 that the sine of 11 pi over 6 is negative 1/2. So we're going to get 2 times negative 1/2 minus the cosine of 2 times 11 pi over 6, which is 11 pi over 3. So 11 pi over 3, there's 3 whole pi radians in there because 3 pi is the same thing as 9 pi over 3. So we're at 3 pi, which is the same as pi, and then we're going to go another 2 pi radians. So we're actually going to be in the 4th quadrant. So we're actually at the same thing as 5 pi over 3. So 11 pi over 3, same thing as 5 pi over 3. So the cosine of 5 pi over 3 is going to be positive 1/2. Which makes me realize that I actually made a mistake in the last one, so we'll go back and fix that. So 2 times negative 1/2 is negative 1 minus 1/2, which we know is negative 3/2 in the previous one. So before, I was wrong when I said that this up here was minus 1/2. It should really be minus a negative 1/2, which means that we're going to change this to a plus over here, which means that this is really negative 1/2. They shouldn't be the same. Sorry about that. I forgot that I had to subtract a negative sign and make them positive. So now all we have to do to finish the problem is find the y values of our endpoints, which was at, if you remember back, at 0 and 2 pi. So f of 0 is going to be 2 times the sine of 0. Sine of 0 is 0, so we get 2 times 0, minus cosine of 2 times 0. 2 times 0 is 0. Cosine of 0 is 1. So we're going to get 2 times 0, 0 minus 1, or negative 1. Doing the same thing, we'll click for 2 pi. 2 pi is really the same thing as the point 0, so we're just going to get back to negative 1. So now let's see which one was our largest y value and which one was our smallest. So looking at all of these points, it's pretty easy to see that 3 is our largest, and then negative 3/2 is our smallest. So for this function, we can write that we have an absolute min at 11 pi over 6, comma negative 3 over 2, and that we have an absolute max at the point pi over 2, comma positive 3. So there you go. That's how you could go about doing this with trig functions. So thank you so much for watching. I hope this helped. Have a great rest of your day.